Okay, so lecture set 4. So again, lecture set 4 is the material or the testable material in lecture set 4 starts on assignment 3. So this will be assignment. I'm spelling assignment with 2 E's. I don't know why. Assignment 3 slash lab assignment 2. Okay, so that's where you'll see the ANOVA stuff. This is not going to be on the lecture quiz. The lecture quiz is going to be lecture sets 1, 2, 3. So the quiz Friday is lecture set 1, 2, 3. Okay, so in lecture set 4, this is still technically this is partially review. So some of you might have seen ANOVA and the F distribution in Stat 151. It tends to vary from semester to semester whether or not it gets covered. And when it does get covered, it's usually kind of snuck in right at the very end. So a little bit of like, this is what the hypothesis test looks like. This is what we're trying to do. Here you go. What we're going to do in this lecture set, so over the next couple of lectures, and maybe next week, depends on how long it takes, we're going to define the test, the purpose of the test, how to run the test. We're going to talk about the F distribution in some detail so that you understand what the table looks like and how to use it. But we're also going to talk about the rationale. So we're actually going to take sort of a deeper dive into the reasoning why we use variances to compare means, which is the purpose of the ANOVA. Okay, so the topics in this lecture set are the F distribution, how we can use variances to compare population means, what or the components of the analysis of variance, and then how we would actually run the hypothesis test, which we call the one-way ANOVA. Okay, so the starting point, we're going to define the F distribution. The reason that we're going to define the F distribution is because we need the F distribution to run the ANOVA. So the hypothesis test that we are going to learn about in this lecture set is utilizes what is called the F distribution. And we will utilize the F distribution the same way that we did the student T and the standard normal. So we will use it to find p-values and we will use it to find critical values. Okay, so what is an F random variable? Well, an F random variable is the ratio of two chi-square random variables. What is a chi-square random variable? It is a sum of n independent standard normal random variables. Okay, so this is the mathematical or theoretical definition of the random variable. From our point of view, the things that matter to us are the shape of the distribution and the fact that it has 2 degrees of freedom, because we need to know the degrees of freedom in order to be working with the right F curve. And we need to know the shape so that we know where to look for information when we're trying to find the p-value and the critical value. Okay, so the F random variable, again, is a ratio of 2 chi-squares. And as a result, you can see that it has 2 degrees of freedom. Okay. So when we are working with F random variables, we will be working with 2 DFs when we're looking for critical values and p-values. Okay, properties of the F distribution. One, it's a continuous distribution. So the same type of distribution as the standard normal and the student T. However, it is a right skewed distribution. So the standard normal and the student T distributions are symmetric about 0. The F distribution is right skewed starting at 0, which means that it only admits positive values. And if you think about the definition given on the previous slide, so the F distribution is found by dividing 2 chi-square random variables. The chi-square is the sum of a squared value. Any value squared is going to be positive. So if you sum n positive values, you get a positive number. If you divide 2 positive values, you get a positive number, right? So it makes sense that the F distribution is a strictly positive value. And as a result, we see it emit a right skewed density curve that starts at 0 and goes all the way up to positive infinity. The parameters or the degrees of freedom for the F distribution are called the DF numerator, which we sometimes call DF1, and the DF denominator, which we sometimes call DF2. The degrees of freedom control the shape of the curve. So the same way that with a student's T distribution, as the degree of freedom went up, the tails would come in and the peak would increase. With the F distribution, as the degrees of freedom change, the peak and the skewness change with it. So those are the parameters of the distribution. Finally, the F distribution is a proper density curve, which just means that the total area under the curve is equal to 1, the same way it was with the standard normal and the student T. Okay, here are 5 illustrations of F curves, and we can use these illustrations just to gain a bit of understanding of how the degrees of freedom can affects the shape of the curve. Okay, so the black curve, which is kind of hidden in the back there, has 4 degrees of freedom for both the first and the second value. The blue curve is an F on 4 and 10. Okay, so you can see that as the second degree of freedom increases, we notice that the peak goes up from the reference. The red curve is then an F on 4 and 30. Okay, so changing the second degree of freedom appears to affect peak height. So the peaks appear to be getting a bit higher than they were with reference to the black curve, and they slightly slant to the right, but they're mainly just increasing. So the tail would be coming in that case. The green curve is the F curve when we change the first degree of freedom. So the green curve is an F on 10 and 4 in this case. Okay, so the peak has shifted over and the tail as a result has gone out. So this first degree of freedom appears to control kind of horizontal peak location, and then the tail is going to change as a result of that. Whereas the second degree of freedom appears to indicate peak height, which pushes the tail in. So the second DF pushes tail in, first DF appears to push tail out. And then the last curve, which is the yellow one, I'll use this because it's hard to see the yellow color. This is going to be when you have 30 and 4. Okay. So maybe we'll just set it up like this. Okay. And then we can see here, so this would be tail in, peak up. So we kind of have like this effect. And then here we have tail to the, or sorry, tail out, peak, sort of down, I guess you could say. Even though with the yellow, it kind of comes up, so it's not an exact relationship, but it would be something like this. Right. So this is the density curve that we're going to be working with when we are working with analysis of variance types tests. And actually, we're going to consider 3 different ANOVA type procedures in this class. In this lecture set, we are going to consider the one-way ANOVA. In lecture set 6, we will consider the completely randomized block design, which is a style of 2-way ANOVA, sort of. And then in lecture set 7, we will consider the 2-way factorial design, which includes interaction. But all 3 of these utilize the F curve. So we will have lots of practice with working with the F curve to find p-values and critical values in order to perform the associated hypothesis tests. Now you can see that in this situation, we have a right skewed distribution, which means that the symmetry tricks that we can utilize for the standard normal and the student T distribution, they no longer apply. But the depending on how you look at it, one of the nice things about working with an F curve is that you always test in the skewed tail. So all of our hypothesis tests are going to be performed here. Okay, so this is the or the rejection region. Or we'll say location of rejection region for all of the associated tests. So we're always testing in the upper tail or the only tail really of the distribution. Okay, so they're all in that sense like one directional tests, if you will. But we'll talk more about the proper way of referring to that in a bit. Okay, so to use or to find p-values and critical values, we have to learn how to use what is called the F table. So like with the student T curve, you have the T table. With the standard normal curve, you have the standard normal table. With the F curve, we now have the F table. The F tables are actually split across 8 different pages, and they are available on the course website. And these tables are utilized in the same way that we use the student T table. So that what I mean is they are most similar to the student T tables. So they give critical values at specific degrees of freedom and significance levels. So our P values will always be bounded the same way they were for when we perform T tests. Okay, so this is an example of an F table. So this is the first page of the F table. So you can see that we have DF numerator, which is DF1 lining the top here. And then we have DF2 lining the side. And then we have our significance level, which is alpha in the second column. So the way that we would use the T table, it's kind of like a 3-way matching game. So we match our first degree of freedom to our second degree of freedom to the significance level to find the critical value. When we want P values, we take our 2 degree of freedoms, DF1 and DF2, and then we consider the block of numbers associated with those degrees of freedom, and then we look for where the test statistic would fall in among that block. Okay, so to illustrate that idea, I have a few exercises at the bottom here. So the first one says, what is the value of F3, 6, 0.05? So this is going to be DF1, this is going to be DF2, and this is going to be alpha. So F3, 6, 0.05 is going to be 3, 6, 0.05, 4.76. So again, just a 3-way match. But for the critical value anyways, it's a 3-way match between DF1, DF2, and the significance level. And I guess I'll just leave it up here for now. Okay, the next one is what is F on 33, 0.01? All right. When we consider the F table, you'll notice that on the first page, our DF1s go up to 9, and on the second page, our DF2s go up to 8. As we scroll through the F tables, we will be able to consider a range of different p-values. So for example, if we load page 2 of the F table, you can see now we have DFs in the numerator, 10, 12, 15, 20, 24, 30, 40, 60, 120. And then we have DF in the denominator, so DF2, 1, 2, 3, 4, up to 8. So on page 2 here, or to find F on 33 and 0.01, we would have to use page 2 because that gives us 30 in the numerator, 3 in the denominator, and 0.01 as the fourth significance level. And that gives us 26.50 as the F value. Right. So when we are tasked with finding our critical values, we need to consider all of the pages to make sure that we can, before we make any adjustments. So what I mean is, if you can't find the exact degree of freedom on the first page, consult the next page, consult the page after that, consult the page after that to make sure that the exact degrees of freedom aren't located on one of those 8 pages. If we are in the event that we cannot find the exact degrees of freedom that we are looking for, then we always round down. And I'll have an example of this a bit later in the lecture set when we look at the associated hypothesis test in detail. But that's the general rule of thumb for working with degrees of freedom. So if we don't have the exact value on the tables, we round down to the closest number. And again, I'll have an example of that a bit later. All right. Question 3. Okay, so in question 3, we're asked, what is the probability f exceeds 0.1 at 3 and 25 degrees of freedom? So this would be an example of finding a p-value using an f-test. So to sketch this problem out, we can start by sketching an f-curve. So our f-curve is a right-skewed curve that starts at 0 and goes to positive infinity. We have an f-value of 0.1, okay? And we want to know the probability that we exceed 0.1. Okay, so we want this red shaded area here to the right of 0.1. All right, so we need to find 3 and 25 degrees of freedom using our F table. All right, so on our first page, we have 3, and again, this page only goes up to 8. Pages 1, 3, 5, and 7 will always give DF numerators of 1 to 9. So we're going to want to consider the odd number pages when we're looking for a DF numerator between 1 and 9. The DFDs, if I recall correctly, they increase on pages 1, 3, 5, and 9 as well. So when we move to page 3, we're likely going to be between 9 and about 16. So we should consider page 5 and page 7 for this particular problem because we want 3 and 25. All right, so if we load page 3, so that, sorry, page 1, page 3, let's try page 5, see what we come up with here. Very close. So you'll notice that page 5 just goes up to 24. So we need to consider page 7. All right. So here's page 7 of our F table. All right, so here's our DF numerator, which is 3. And here's our DF denominator, which is 25. Okay, now to find the p-value, we are going to work within the block of numbers that are given here. Okay. And that means that we're going to use these alpha values to bound our p-value. All right. The value of interest to us is f equals 0.1. We can see that as we move down the column here, we go 2.32, 2.99, 3.69, 4.68, 5.46. So we're increasing in f value. Okay, so our value is going to sit here, f equals 0.1. So since we are larger than the smallest f value that's given here, that means that our area to the right must be larger than the largest alpha value given here. So the way that we read the F table is the same as how we read a T table. So we would have a sketch that's like this. We would have a right skewed curve. Oh, that's too symmetric. We would have a right skewed curve like this. And this little quantity here, which I'll sketch in blue, this is going to be the alpha. Okay, so the table is giving us area to the right of the F value. So our F value is 0.1, which is smaller than 2.32. So our area to the right of 0.1, so the area larger than 0.1, must be greater than 0.1. So all we can say here is that based off of the table, this area is greater than 0.1. So the probability that F exceeds 0.1 is greater than 0.1. And in hindsight, I realize using 0.1 was probably not the best idea because it's getting repeated a lot, but the value inside is the F value that sits on the axis, and the value on the outside here, this is the largest tail area that we can work with given the structure of the F table. So let's look at a second example to try and clarify this idea. So in question 4, we have find the probability that F exceeds 4.5 on 4 and 13 degree of freedom. Okay, so here's our F value. This is going to be 4.5, and we want this red shaded part here. So this is what we're interested in. Okay, we are on 4 and 13 degrees of freedom. So this is going to be, of course, it's going to be a page I haven't loaded yet, but page 3 of our F tables. Okay. So we have 4 in the numerator. We have 13 in the denominator. Okay, so we're going to work with this block of numbers here and this block of numbers here. Okay, our F value is 4.5. So we are going to sit here between 4 and 5.21. So our F value is in between 4.00 and 5.21. Okay. So that means that our area is going to be between 0.025 and 0.01. So we can say, well, so going back to our slide, we can write that this area here is between 0.01 less than area less than 0.025. So then we can say 0.01 is less than the probability F is greater than 4.5 is less than 0.025. And again, so this is what we will typically expect when we're finding p-values using the F distribution. Does anyone have any questions? Sorry, pouring tea real quick. Slow process. Okay. All right. So what is an ANOVA? When do we use the ANOVA? Why does the ANOVA work? Our ANOVA procedure is essentially the general extension of our 2-sample hypothesis tests. So in lecture set 3, we learned how to conduct 2-sample hypothesis tests to differentiate, or rather to determine if there was evidence of a statistically significant difference between 2 means. We also did the directional test greater than or equal to, but the general idea was comparing 2 population means. The ANOVA is an extension of this procedure that tests for a difference among 3 or more means at once. So the ANOVA is the general extension of the 2-sample test to the situation where you have 3 or more population means that are of interest to you. So for example, in table 8, what we have here are estimates of the lengths of minke whales that were trapped at different depths in the East Sea of Korea. Okay, so each depth here forms, we can think of it as like a sample or a group. We're going to establish terminology for the ANOVA in a little bit. We usually refer to these as treatment groups. Okay, so we would have here for treatment groups. These are also called levels. There's a lot of terminology that gets thrown around, but basically we have four different representations of 4 different population means. That's kind of the idea. You'll notice that in the table, we have summary statistics for each of the different depths. So we have the number of whales that would have gotten caught. That's our sample size. So 39 whales were found between a depth of 0 and 49. 20 whales were found between depths of 50 and 99. 28 whales were found between depths of 100 and 149. And 14 whales were found between depths of 150 and 199. We have the average length of the whales at each of the depths, and we have the standard deviation for those whales at each of the depths. So we have our usual summary statistics. Okay, so the question is there evidence of a difference in mean minke whale length between each of the 4 depths? So that's what we want to know. And that's the purpose of the ANOVA, is to answer that question. So formally, what we are testing is that the 4 means, so the mean for each depth, are equal against the alternative that a difference exists among at least 2 of the means. And we'll see formal definitions of this in a little bit, but this is the purpose of the ANOVA. So general search for differences in population means when you have 3 or more means. So it's an extension of our 2-way procedure. All right, so again, the goal of the experiment is to determine if there is a difference in the average body length among the 4 or between the 4 different depths. Okay, so you can think of mu1 as being the mean for depth 0 to 49, mu2 as being the mean for depth 50 to 99, etc. And we want to know if a difference exists between mu1, mu2, mu3, mu4. To answer this question, we use the ANOVA, or the analysis of variance procedure. In particular, we are using what is called a one-way ANOVA because we only have one variable that is of interest to us, which is the length of the whale. Now, the ANOVA procedure, unlike the student t-test that we looked at before, is a test that only considers the variation in the experiment. And in fact, what it does is it compares 2 types of variation. And we're going to talk a bit about that as we progress through the set. Now, what's interesting is, despite the fact that we are analyzing variation, we are using the variation to determine if there's a difference in the means. So how does this work, and why does this work? Let's consider a very simple illustration, or 2 very simple illustrations. All right. So illustration Z first. In this illustration, we have 2 independent samples, which I call sample 1 and sample 2. I know, creative names. The first sample are the black circles that are located on the grid. Okay, so here, 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 and here. And the second sample are the red crosses, here, 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 and here. All right. So these 2 samples were collected from populations with 2 different means. And you can see from the summary statistics that these means are fairly well spread out. So we have X bar 1 at around 16.85. Okay, so X bar 1 is going to be about here. And we have X bar 2 at 25.30. So that's going to be about here. Okay. Now the question is, from looking at this plot, does it look like mu1 does not equal mu2? So we've generated samples from populations with 2 different means. So mu1 is probably in the area of about 17, mu2 is in the area of about 25. So these are different values. we look at this we visually inspect the data, and we're asked, does it look like mu1 does not equal mu2? Well, I think the answer here has to be no, right? So even though, so despite the fact that the samples come from populations with different means, we can or we can't tell that they are two different samples. Okay. Now, if it isn't clear to you why you can't tell their samples, imagine there wasn't a color coding and every symbol was the same symbol and they were all the same color. Then it would just look like one line of observations that exist together, right? So what we're showing here is that since the within sample variation, okay, I'll make this 0.1 and this 0.2. So since the within sample variation is large compared to the between sample variation, the difference in means is hidden. Okay, so let's just go over this idea. We know that we have generated data from populations that have different means. Okay, so sample 1 comes from a population with a mean of like 17-ish or around 17. Sample 2 comes from a population with a mean of say 25. When we plot the data, we're asked, does it look like they are samples with two different means? So does it look like you can distinguish between mu1 and mu2? Well, if there was no color coding and we weren't told which observations belong to which sample, you'd have to say no. And the reason you'd have to say no is because the variation within the sample is larger than the variation between the samples. Now, what does that mean? Okay, so if we consider the black circles, we can write that they have a spread that exists, or let me draw this, the symbol a little bit better. Okay, so the black observations have values from here, so this is the min, to about here. Which is the max. And then we can say that this line here represents within sample variation. Okay, so when I'm talking about within sample variation, I just mean the variance or the spread of each of sample 1 versus sample 2. So within sample means for the particular sample. And then if we look at the red points, it's a very similar idea. So you can see that we're ranging from about here to here. Okay, so this represents within sample variation. Okay, now what we're saying is the within sample variation is larger than the between sample variation. What is the between sample variation? Typically, we assess between sample variation by looking at the spread between the means. So we can say that the between sample variation is the difference or the spread between the two means here. Okay, so this represents between sample variation. Okay, so each sample has its own variance. And now we're also considering the variance that represents, or the variance between the sample means themselves. And we call that between sample versus within sample. And the argument that we're making on this slide is that because the within sample variation is too large when compared to the between sample, it masks the fact that we have different means. All right, so let's look at a situation where we decrease the within sample variation. So example 2 is the same idea. So we have x bar 1, let's say its mean is around 17. We have x bar 2, its mean is around 25. Now we plot that data. Does it appear like these two samples represent populations with different means? Well, even if we didn't have the color coding and they were just two different groups, we would be able to write yes, we can distinguish between each sample, right? So we can see that we have mu1, or we have sample with a mean of about 17 here. And then we have the second sample with mean over here. But that doesn't really make sense on the scale. So it would have to be over here slightly. Okay, so we can actually tell there's a difference. And what is the only difference between this illustration and the previous illustration? Well, now the within sample variation is small compared to the between sample variation. Okay. So the fundamental idea behind the analysis of variance is that we want to compare two kinds of variation, what we call within sample variation and what we call between sample variation. So given an entire experiment, we calculate these two types of variance, and then we compare them to each other. And if the between sample variance is larger than the within sample variance, this would provide evidence that a difference might exist. Whereas if the between sample variance is small compared to the within sample variance, this would likely provide no evidence that a difference exists. So we are using variation to make a decision about the potential difference among a collection of means. And as I previously mentioned, the ANOVA considers 3 or more means when it is being applied. So these illustrations are just simple illustrations that are meant to try and communicate why we can compare variation to make a statement about the means. But when we actually run the tests, we would have multiple samples, 3 or more samples on our plot that we would be utilizing to compare the means. Okay, any questions? Okay, so here's the same plot, and now we have both samples put on the same page. So you can see the differences between example 1 and example 2 in terms of the variation of the samples. And again, this plot, or this slide, is summarizing what I was trying to express before flipping to said slide, that if we consider the two types of variance, so the within sample, which would be this part, and then this part, to the between sample, which would basically be from x bar 1 to x bar 2. Okay. And then here, we would have x bar 1. We would have x bar 2. Right? You can see that the within sample variation in example 2 is much smaller compared to the between sample variation than it was in exercise 1. And that is how we're going to determine if there's a difference among the means, by comparing these two types of variance. All right, so what is a one-way ANOVA? A one-way ANOVA is the simplest type of ANOVA. As I mentioned before, we're going to look at 3 different analysis of variance procedures in this class. We call a one-way ANOVA a one-way ANOVA because we're only considering one factor at a time. So in our particular illustration, we are measuring whale length. So that's our variable. And we have one factor, which is depth. So the factor count influences the type of ANOVA you use. So the 1 in one-way ANOVA means one factor of interest. If we were using a two-way ANOVA, it would mean that we have 2 factors of interest. The treatment groups, or the different population representations within the sample, can also be called levels. So sometimes when we use ANOVA, we will think of our factor as being what splits the data into its groups, and then the number of different groups are called the levels. So we have terminology that kind of overlaps with each other, but the idea is we're comparing means across the different levels, which is the same thing as saying we're comparing, for example, here, 4 different population means. Okay, the variable that we are measuring, so for example, body length of the whale, we sometimes call this the response variable. The reason why we would call it the response variable is because there's a relationship between our ANOVA model, we'll talk about this a bit later, and linear regression, which we'll talk about much later. So the response variable notation, at least as far as I see it, is a fallout of the link between the one-way ANOVA model and the general regression model. But for our purposes, the variable is the thing that we are measuring. The response variable is the same thing. We've already defined the factors. So this is basically just the variable that splits the data into its groups. The factor levels are just the different designations for each level of the factor. So in our situation, one factor level is 0 to 49. Another factor level is 50 to 99, etc. Treatments refer to the factor level combinations. In a one-way ANOVA, the treatments and the factor levels are the same thing. In a two-way ANOVA, there are interaction effects, so it creates extra treatments, but we'll see examples of that a bit later. Again, there's a lot of notation that means the same thing in the context of this particular procedure. Okay, so let's just talk a little bit about how we can expect to visualize data when we need to use an ANOVA. The big giveaway is that we are going to have a data set, so we'll have one variable that's split across 3 or more groups. So if you think about an SPSS data file, on assignment 1, we had a variable which was, I forget what the variable was measuring, but you had rural and urban. So you had 2 different classifications of this one variable. Now imagine you had rural, urban, subrural. So you now have 3 different classifications. That would be an example of what a layout for a one-way ANOVA might look like. Another example could be if you have 4 different columns that represent different treatments within the same experiment. That could be another illustration. So ANOVA data can present itself in a couple of different ways, but the big giveaway is that your data is being split across 3 or more different groups or factor levels. Okay, so it is possible that we might observe the following table, which would represent the data in our experiment. So you might have, for example, for population 1, and you might have a sample of size N1, and then you have your sample statistics. Population 2, you have a sample of size little n2, and then your statistics. And then that same idea for all K populations. Now from that, we can define a number of different variables and summary statistics using a new indicator. For the most part, we don't need to concern ourselves with this too much, but I'll go over these declarations on Wednesday anyways, just so that we have an idea of how that we can start differentiating between observations within an experiment. Okay, so I'll stop there for today. On Wednesday, we'll continue with our study of ANOVA. And again, on Friday, we have our first lecture quiz, which will be held during the class hour and administered through CrowdMark. So if you guys have any questions, as always, please let me know. And otherwise, I will talk to you on Wednesday afternoon. Yes.